Hey everybody, welcome back. This is the fourth video in the genetic algorithm series, and in this what we're going to do is take the stuff we finished in selection and we're going to reproduce and build a new population, or build a second generation of backpacks, and hopefully those backpacks will be better than the previous generation. Now in the selection stage, if you remember, we took all the backpacks. We had 100 of them to begin with. We got rid of some of them because they were overweight. They were over our max weight of 15. And that got us to about 50 backpacks, it seems, somewhere between 40 to 50. And then we took that list of backpacks and we sorted them by the cost. So at the moment, what we have is a list where the lower indexes are the higher cost and the higher indexes are less. It could even be a cost of 0. They could be an empty backpack. So what we're going to do now is we are going to do reproduction, which is going to take in the backpacks and the population size. And we're going to make a new function up here, selection, define, reproduction, and we got backpacks and population size. Now, to do reproduction, we are going to use something called a triangular distribution. And I want to give you an idea of what that looks like first. So it is in the random module. So I'm going to import that though. It's not triangle, it's triangular. Okay. And triangular it's just like random, except it's getting, instead of getting numbers with equal probability from 0 to 1 or random int 0 to 20 or whatever, it's actually going to get it in a different distribution. And so if you're not familiar with a probability distribution, hopefully this little explanation will make sense. So let's say that I go ahead and I make a list. So I'm going to make a list, and this list is just going to be, it's going to have, let me put some more things in here. There we go. So this list has, we got 9, I'm going to put one more. I've got 10 spots in this list. And what I'm going to do is I'm going to say for I in range, and I'm going to do 1,000. Now, if I was using random int and I said, not list dot append, but list random int 0 to 9. So I have 0 to 9 indexes here. If I did this and I added 1 to it, what do you think the final list will look like? Well, I've got 1,000 things here, and I've got 10 possible buckets to put them in. And I should get something where it looks pretty close to having 100 things in each of these buckets, right? So if I run this, we get about 100 things in each of the buckets. And that's good. That's what it was called, just like it's just an even distribution. So everything gets the same probability of being called 0 to 9. The thing is what I want is I want this side of the list to actually have bigger numbers. I want this to be, like 400, 350, and so on, all the way down. And this side, maybe just 5 or 6 over here. Because if you remember, the start of my list in my backpacks is where the good backpacks are. And when I do reproduction, I want to randomly grab from that side of the list more than I want to grab from the end of the list. So the start of the list I want to focus on. On the end of the list, I want to give it a chance to get called, but I want it to be a very low chance. And that's where the triangular function comes in. So triangular will give us a number. So I'm going to say 0 to 10 here, and these first two numbers give us the range from 0 up to 10, and then this will be 0, which is going to be the mode, or the most often number that I want called. So 0 is, everything's going to tend to be towards 0. So if you don't know what I just said, take a look at the documentation for triangular. Essentially, this is just like random int here, 0 to 10, but this is telling it what to be called the most. So 0 will get called more, and then everything as I go from 0 towards 10 will get called less and less and less and less. Now the problem with this is triangular actually returns in it doesn't return integers like random int, it returns floating point numbers. So if I try to run this, I'm going to get an error, and it's going to say something about the index here. So must be integers. I can't actually index it. So I got to convert this to an int here. So let's just go ahead and convert to an int. And if I run this, what you see is it actually gradually goes down from this side to this side. So this end gets way more focused. If I run this again, I'll probably get something better. So this is the highest possible, and each time I go further to the right, it gets less and less. And then actually the possibility of getting something that fits in the 9th index is really, really low. And I can run this multiple times and we'll always get similar values. This is what I'm going to use because this is going to help me call those backpacks on the left side of the list or the start of the list more often than those on the right side of the list. So let's see how it works with the backpacks. I'm going to delete this, and let's go ahead and delete all that. And let's go ahead and pull out each of the backpacks. So I'm going to make new backpacks. These are the ones that are going to, after we cross over, I'm going to stick my new backpacks in there. I'm going to say while the length of new backpacks is less than the population size. Okay, so I want to get my population back to 100. And if you remember, the population is somewhere sitting around 40 to 50 right now. Backpacks is a length of 40, 50. All right, so I'm going to pull out each of the backpacks, and I need to get 2 backpacks in order to do my crossover. So I'm going to say backpack 1 is equal to the backpacks list. And I'm going to do the exact same thing I just did, triangular. And it's going to be 0 up to the length of backpacks. So I'm going to take the whole list of backpacks. I'm going to take here. So this could be 0. This could be maybe 52 or something. And I want those on the far left side or close to the 0 index to be called the most. Okay, and that gets me backpack number 1, and I can just copy that down, and that gives me backpack number 2. So I call backpack number 1 backpack number 2. It's possible that backpack number 1 and backpack number 2 are the exact same backpack, but it doesn't really matter. I'm not going to try to not have that little problem. It's not really a problem so much as it's just going to end up with a duplicate backpack at the end, which is okay. All right, so this should work just fine. Oh, I'm going to end up with a small problem here. We'll just move on. Let's break out there. There we go. So this right now gives me backpack 1, backpack number 2. Now I need to find the point where I'm going to cross these over. So I'm actually going to use, it's going to look kind of like this. I'm going to pick a point here on the first one, and I'm going to take this point here. Let me move this. Maybe make this star, star, star. Oops. And this dash, dash, dash. And this star, 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 star. So if you imagine this is the first backpack and this is the second backpack, I'm going to take this half of this list and this half of this one. I'm going to combine those two together, and I'm going to do the same thing for these two. Okay, so let's make a splicing point. Let's call it the crossover point, actually. Crossover point is equal to a random integer, and I don't want to take the whole one, so I'm gonna at least have one of the individual genes for each one, and the length of backpack 1 minus 2. So minus 2 is gonna get us so that we are not taking the very last element. So that's the crossover point. And I'm gonna say new backpacks dot append, and I'm gonna take the first half of backpack 1. So the first half of backpack 1, and I'm going to go from 0 up to the crossover point, and I'm going to cut that together with backpack 2, and it's going to go from the crossover point to the end of the list. And actually the nice thing is I can copy this And I can do the exact same thing with the second one. I just need to swap the sides. Okay, so this is going to go ahead and give us the both backpacks, and we take each half of each one of those backpacks and cross them over, and we end up with 2 new backpacks added to our list. All right, so I go ahead and add those, and I'm good to go, and I can return new backpacks. All right, so let's make sure this all worked here. Let's go ahead and for backpack in new backpacks, and let's go ahead and print out backpack. Let's run this. Okay. We have an issue. I think I've done something wrong on my crossover here, so let me take a quick look. Oh, not 0. This needs to go from the crossover point to the end. That's my fault there. Shouldn't have been a 0 there. I should have just done from crossover default to the end of the list, and that should fix our problem. Okay, good. So we've got all these new backpacks here, and we should have 100. Now, if you change your population size to be an odd number, that might be a problem because the population size will change based on here, because we're going to have even numbers added every time. So you can do one more thing in order to make sure that everything is exactly the right population size. It's just take all of those, anything that's over the size of the population, any additional backpack you might have added, just cut them out, get rid of them. Okay, and that is it. That's entirely reproduction. So let's walk back through it really quick. All we do here is create a new list for our backpacks. We're going to keep doing our while loop while the population size is not what we want it to be, which in our case is 100. We use the triangular function to pull out 2 random backpacks, preferencing those towards the start of our list. We randomly pick a crossover point, and we make sure that we leave at least 1 gene on the left or the right side. So those left and right genes, it makes no sense to cross those over. We'll just get the same backpack back if we do. So we'll make sure the crossover point is in the middle somewhere, and then we append them back to this new backpack list after we do the crossover, and that gives us our new backpacks. So we're down here, we've got everything done reproduction wise, and we need to move on to the final stage, which is mutation, which we'll do in the next video. So I will see you then. Thanks for watching, and if you have any questions, leave them in the comment section below.